Okay, so today I'm gonna explain you best approximation solution for a 2 by 2 matrix. So here, first of all, let me explain what is a best approximation least square solution or least square best approximation solution. Suppose if you are given with a linear system Ax equal to b and you know that it is inconsistent. So when it is inconsistent, now one is looking for its solution. Yeah, if it is inconsistent, how can you look for its solution? Yeah, the intention is like, am I able to find a guy for which the norm of ax minus b equal to, this is the minimum. Means what I can say, this one is an approximate solution, approximately, or like ax is approximately equal to b. It's not exactly equal to b because the system is inconsistent. Okay, so now we are going for an approximate solution. So now here, so our aim is this: we need to find a y in such a way that the norm of ay minus b, this function, is the minimum for y, right? So here, let me explain this expression for a 2 by 2 matrix, which will be very clear. So now if you take a linear transmission from R2 to R2, okay, and it will be given by a 2 by 2 matrix, right? So here I'd like to have a linear system that is Ax equal to b. Right? Now here I am taking a linear system in such a way that this linear system is inconsistent. So if I take a 2 by 2 linear system, when can it be inconsistent? We know that it will be inconsistent when the rank of the matrix is 1 and B does not belongs to range space of A. So if I have these two conditions, then I can say that this matrix is inconsistent. Okay, this linear system is inconsistent. Now, what is our aim? We'd like to find a vector for which the norm of Ax and b is Ax minus b is minimum. Okay, so first of all, let's try to understand what is the action of A geometrically. If you have a linear transformation whose rank is A, let us see what happens. So here we have a transformation between two spaces, both are same, R2 to R2, and that transformation is given by A, right? Now you're saying that it is I should take a matrix of rank 1. It means you can see that the rows are constant multiple of other, or one row is a constant multiple of other row, or you can think like one column is a constant multiple of another column. So let me talk in terms of columns. That will be helpful in future too. So 1 comma 2, you can take this one as 2 comma 4. You see that this is the matrix of rank 1, right? And here you see the first column, if you multiply first column with 2, you are going to get the second column, right? And if you multiply the first row with 2, you are getting the second row, right? So it is clear that it is a matrix of rank 1. So here, now let us see the image of what is the image of entire R2 under this mapping. Now you can see that if you multiply this guy with x comma y, so I'll end up with this expression, that is x plus 2y, and here I'll have 2x plus 4y. So what I have is if I take this entire expression to be u, and this is 2 times of u, so this is nothing but, if you take u out, 1, 2. Now you can see this space as a space generated by the element 1 comma 2. So now where is the vector 1 comma 2? 1, 2, right? So somewhere here. Now the image of this entire R2 is nothing but a line like this, a line passing through origin. So this is what. So now if I take any vector b which is from this line, then I can say that Ax equal to b is consistent and it has a solution. But whereas if you start with a b which is not in this line, it means let's say if I take this guy like this, I have taken it to be B. Now can you find any vector here whose image is equal to B? No, it's not possible, because we know its entire image lies on this line only, right? Now what is it we look for now? Now if you cannot find the solution exactly, can you give me a vector whose image is near to B? Whose image is near to B? Near to B, it means where do you take? Are you going to take here? No, it's far from B, right? So definitely what do we take? Like you have a line and you have a vector. So can you give me a point on this line which is nearest to this vector? So what do? Obviously you go for the perpendicular a vector. In other words, you just project that vector onto the space. So the moment you project this vector onto the space, like here I have, right? So now, this is the vector, like you try to take a vector x for which ax equal to this guy. Let me call this guy as C. Ax equal to C. Now I can see that the distance between C and B, this is minimum. So the distance between C and B is the minimum vector, right? So here, now what is our aim? Well, we need to see what is that x which contributes ax equal to C. Now the question is, how many x are there? Is it unique x or infinitely many x? Yeah. So let's see. So what is your guess? So we know that this linear system, and when a rank is 1, right, and if this b it is inconsistent, you know that it is going to have, right, like if C is coming from this space, it is going to have infinitely many solutions. So here you can see that the pre-image of C will have infinitely many vectors, right? So if it has infinitely many vectors, then okay, I'll tell you. For example, I'll take this B to be 1, 1. Okay. So let me see what are like if you project this guy to 1, 2. Oh, I might have started with a difficult expression. Oh, fine. So let me see what is a projection of 1, 1, like 1, 1 onto what is that vector? The vector is 1, 2. This is what I started with, right? So now you need to see the orthogonal projection of 1, 1 onto the vector 1, 2, right? So now what is the orthogonal projection? You have a formula. Do you remember? Like projection of A bar onto B bar, that's nothing but A bar dot product with B bar divided by, right? You're projecting A on the direction of B. So now this is nothing but, now you want it to be in the direction of B. So mod B, and this is mod. Okay, so this is the component, it is what exactly represents the size of the vector, and this represents the direction. I'm projecting in this direction. Okay. So now let us try to find what is A dot B, like 1 times 1 plus 1 times 2, that is 3 by its magnitude, the magnitude of B. So that is 3 by square root of 5 into, like this is 1, 2 by square root of 5. So what do you get? You get 3, 6, 3 by 5, 6 by 5. So now this vector is nothing but 3 by 5, 6 by 5. Okay, so this is the projection of 1, 1 onto the vector, like what is it? 1, 2, right? Now what is our aim? So we need to find a pre-image of 3 by 5, 6 by 5. So what is the pre-image of 3 by 5, 6 by 5, right? So here I'll do one thing. I'll take 3 out. So if I take 3 out, So this one I can see like 1 by 5 comma 2 by 5. Of course I can take 3 by 5 out, 3 by 5 out, then 1 by 5, sorry, 1 comma 2. So now here this clearly tells what must be u must be 3 by 5. But what is u is equal to x plus 2y. So x plus 2y, that is equal to 3 by 5. Now how many x comma y's are there for which x plus 2y equal to 3 by 5? Every point on this line, every point on this line, right, satisfies this condition, right? So we have infinitely many such x for which ax equal to c, or ax equal to 3 by 5 comma 6 by 5. So how many solutions we have? So we have infinitely many solutions, because those solutions will be given by this equation, x plus 2y equal to 3 by 5. Now the question is, what is the vector on this line which has a minimum norm, right? I need to find a vector on this line, it has a minimum norm. So now what is that vector? Or this is same as saying that a point, just find a point on this line which is near to the origin, right? So that will have a minimum norm, obviously, right? Why? Because you can see this geometrically, like, so x plus 2y equal to 3 by 4. So x equal to 3 by 5 somewhere here, and this is 3 by 10 somewhere here. Let me take this one here, this one here. So now this is that line. Now what is a point on this line which is near to the origin? So that's what I need to find here. Okay, now this is where you can see the importance of Lagrange's multipliers, right? You have done these problems in Lagrange multipliers, like finding a point on the plane which is near to the origin, right? So here, if I look at that point, so now I should tell what is that point, right? So how do you get that point? So let me use Lagrange multiplier, or you can use just an orthogonal projection of 0, comma 0 onto the line x plus 2y equal to 3 by 5. But okay, let me use this guy, that is x square plus y square plus lambda into like x plus 2y minus 3 by 5. Now 2x plus lambda equal to 0, 2y plus 2 lambda equal to 0. So now you can see that x equal to minus lambda by 2 and y equal to minus lambda. The moment I substitute it here, so I'm going to get minus of what I get here, lambda by 2, right, minus plus 2 lambda, that's equal to 3 by 5. So now if I take LCM, so what I get is 5 lambda by 2. So we take it to the other side, this implies lambda equal to minus of negative 6 by 25. Negative 6 by 25. Now therefore x is equal to minus 3 by 25, minus it to minus plus, and y equal to 6 by 25. Okay, so 3 by 25 comma 6 by 25 is the vector which has the minimum norm on this line. So therefore, so what is the best approximate solution for this guy? So the best approximate solution for this guy is nothing but this is what, 3 by 25 comma 25. That's it. So this is the best least square solution for the given linear system. Okay. Euclidean norm, that is why we are calling it as a least square solutions. Okay, so let me see what is its Euclidean norm. So Euclidean norm is nothing but it's same as its norm, right? I mean 1 by like 625 under root, that is going to be 25, and this is a square root of 9 plus 36. How much it's going to be? So 45. So square root of 45 by 25 you can say this is 3 root 9 times 5, right? 3 root 5 by 25. Okay, so this is what. Now let me take a vector here. Let me take 3 by 5 comma 0. This is a point on this line. So now what is its norm? Its norm is nothing but 9 by 25. So now which one is greater? Which one is greater? 3 times root 5 by 25 is greater, or this is greater? So only thing I need to know, I need to compare 3 and 9 root 5. So this is 3 and root 5. So 3 value is 3, root 5 value, it is less than 3. So therefore this is smaller. So now this is the best least square solution of the linear system. Okay, so this is all about it. Okay, I hope you understand what is the best least square solution, and you can see that geometrically, like this is what for a 2 by 2 matrix, and similarly you can extend this result for a 3 by 3 matrix as well. So there, if you have an inconsistent linear system, so the possibilities are, it may have the no solution, sorry, inconsistent, it means no solution only, right? So if you take an inconsistent linear system, there is no solution. It means, like, I know the rank of the matrix is either 2 or 1. If it is a 2, then it will be a plane whose image, and if it is 1, it will be a line. So now what you are doing, you are actually picking a vector which is neither on this line or plane, like whatever may be the image. You are not taking a vector from the image set. So definitely, if you do not take a vector b from the image set, then ax equal to b will not have a solution. If it doesn't have a solution, then we look for a best least square solution. So what do? You take that guy, just project it, right? You just project it onto that plane. So now you take the projected vector. Now you look at its pre-image. Now in that pre-image, you look for a vector which has a minimum norm. So that is the best least square solution. The same idea, you can generalize it to n-dimensional space. I hope you got it clear. Yeah, thank you. Bye.